Terry. Please go ahead.
Okay. Hi, my name is Terry. I'm from National University of Singapore. So today I'm going to present our papers on MURAVE. It's a new rank code-based signatures with multiple rank verifications. So just an overall view for my presentation today. So I'll just give an introduction and motivations for our work, and then I'll describe our signature scheme MURAVE, and then I'll talk about some of the security and the problem assumption in our signature scheme. And lastly, I will discuss the performance of our signature scheme and also do some comparison with some other signature schemes. So what is a signature scheme? Basically, a signature scheme is an algorithm that consists of 4 sub-algorithms. So the first one we have is a setup algorithms to set up the parameters, and then the key gen algorithm is to generate the public verification key and also the secret signature key. And the next algorithm is the signature, the sign algorithm. It means we are given the signer will have a message M, and it's supposed to sign a message under the secret key. And then finally, the verification algorithms to check whether the sigma, the signature is a valid signature on the message M or not. So basically, in just an overview for code-based signatures, this is basically there are 3 main approaches. This is not the exhaustive list. So the first approach is the hash and sign signature, and the second approach is proof of knowledge signatures. So basically, it is we apply the Fiat-Charmé transformation to the identification protocol to convert it into a signature scheme. And the third type is something like a Schnorr type signature scheme. So what we are particularly interested in is this Schnorr type signatures. So I'm now giving some examples in Schnorr type signatures. So the first one is in hemimetric we have Peschietti's one-time signatures, and also one of the summation to NIST RACOSS. So for rank metric there are 3 constructions of this type. First is TPL, the second is RQCS, and the third type is Durandal. And as you can see over here, the red is one, those signatures that has been attacked or being broken. So we have only the only one that's still secure up to date is the Durandal, the rank metric signature scheme. So the question is, are we able to construct other secure Schnorr type signature scheme in code-based setting? And of course, we want to achieve what we want to have is to have a compact key size. So here are some terminology before I move on. So we consider FQM as a finite field with QM elements and an irreducible polynomial of degree k, p. And now let's say we are given, we consider a vector G of k tuples in FQM. So we can view this vector G as a polynomial Gx with each of the coefficients over the Gi. And now we are given 2 vectors G and H, and I denote this G multiply H as the multiplication of these 2 polynomial Gx and Hx over modulo of this P. And the next one will be, let's say I can find another polynomial such that G multiply this polynomial is equal to 1. Then we call this vector as a G inverse, and we call G as a invertible polynomial. So now I'm going to give a rough idea on how do we apply the Schnorr approach in rank metric. So I'm just quoting one example of this RQCS signatures. So if we consider an ideal code, 2KK ideal code with a parity check matrix, H generated by polynomial 1 and H and P. So basically, the public key for this signature scheme is the parity check matrix H and a syndrome S. So the syndrome of this S is computed by multiplying E and H transpose. So this E, essentially, we are choosing this E over some polynomials with low rank. So I'll give the definition for rank later. And to sign a message, basically, we will need to choose another ephemeral key U with a low rank, and then we compute this Y equals to U H transpose. then we set the hash function, set the hash of this y together with a message to be committed, and we set it equals to C. So this C is set to be as a vector in F. So F here is a subspace of R dimension, and finally we will send out the signature Z, which each of the Zi is equals to Ui plus C multiply Ei. So these are all polynomials over modulo K. Over modulo P, sorry. So finally, we will send out the signature sigma, which is equals to CZ. And to verify whether this signature is a valid signature or not, what we need to do is we need to check whether the rank weight of the Z is less than equals to this inequality or not. So the purpose of this is to make sure an adversary is not able to forge the signature, because an adversary can just look at this part, this syndrome, and compute some high rank polynomials, and they can easily forge S. So we need to check whether the rank of this is less than equals to these conditions. And finally, we will plug in this Z1 plus Z2H minus CS into the hash function and check whether is it equals to C. So here are some more terminology before I move on. So I denote this square bracket as a linear span of the elements inside. So in fact, we can view this FQM as a linear subspace. So this linear subspace has a basis beta 1 to beta m. So yeah, in other words, this FQM is a linear space of linear span of all these elements. And now let's say we are given a vector in FQM, and now we define this support for this vector X as a linear span of all the elements inside. So basically, this support X is just a vector subspace, and to define the rank metric on this vector X is just essentially the dimension of this vector subspace. And the next term is support basis, just a basis for support X. And finally, this is the last term, which is if you are given two vector subspace A and B spanned by all the elements AI and Bj. So now we define a product space of A and B as the span of all the elements AI, Bj. So basically, we just take each component from A and B, then we can form the vector subspace spanned by all the elements here. Okay, so here are some attacks on this. There are some challenges in adapting Schnorr signature in rank metric. So if we are given this signature C and Z of this form, so what we can do is we can compute the support of this C. We can compute the vector space spanned by all the elements here. And then we can also compute support of Z, which is spanned by all the elements here. So this attack aims to determine the secret key support E and also support U. So what we can do is we can use techniques from the decoding of RRPC, and with high probability we have support of this on the left is equals to the support E. So basically the idea is we multiply the inverse of all the bases in support C, multiply it into the basis for the support of Z. Then we take all the intersection of it, then we can have this support of E. So in other words, the signature will leak information from the secret key. So now I'm going to describe the ideas for our signature scheme. So basically, this is the signature construction for RQCS. So I've used some colors here to denote to do some comparison for my scheme and the RQCS. So the idea is now similarly as in RQCS, now I'm going to add another extra term over here, which is S prime. So this S prime is equals to E plus FEH. So these are taken over some low rank vectors, low rank polynomials. And then we want to compute this gamma equals to Y1 plus Y2H. So similarly, what we do here is we have Z1 equals to Y1 plus C, the purple color one. This is the secret for the first component. And what we want to do here is if we just compute C and W eta U together, and in fact this will leak out the secret for the informations from here. So what we are going to do here is we will include this polynomial tau. So this polynomial tau will hide the structures, the secret W with these structures. And then we will include another term, the secret here over E, and another term phi. So what is the purpose for this phi? So I'm going to simplify these equations, and then what we want to achieve over here is we want to make sure the underlying term will become 0. So essentially phi is just equals to minus lambda rho UE inverse. And this will make Z1 just equals to A. So all the secrets over here will disappear. So for Z2, similarly, we will do the same thing, Y2 plus C tau WV. So we multiply this together and then plus phi FE. And then we will simplify the term, and finally we will have Z2 equals to B plus lambda V double prime minus U double prime F. So essentially the purpose for this is the information on the secret lambda U, the underlying one, will be hidden by the vector phi, and also the information on the secret V plus U dot F will be hidden by the vector lambda. So that's the rough idea of this constructions when we generate signatures. And then to verify the signatures, what we need to do is we need to check whether the rank of Z1 equals to RA and rank of Z2 is less than or equals to this term. And finally, we will also need to check whether rank of tau and D are they equals to K or not. And finally, we will need to compute this term, which is similar as the RQCS. We plug in the terms inside and check whether it is equals to the signature C or not. So basically, we need to perform multiple rank verification so that the signature forgery could be prevented. So that's why we call our signature scheme as a MURAVE. So in our signature scheme, we also relies on some of the hard problems in rank metric coding theory. So the most common one that we use is the rank syndrome decoding problem. So basically, it is the rank version of the syndrome decoding problem in the Hamming matrix. So basically, we are given a syndrome S equals to XH transpose. Are we able to determine this X of low rank? So that's the rank syndrome decoding problem. And also our scheme also relies on the difficulty of ideal LRPC codes in distinguishability problem. So given a polynomial, let's say we are given a polynomial H, so we are supposed to distinguish whether this H is just a random vector or it is of the form of X inverse Y, where X and Y are polynomials with low rank. So these two are some existing known problems in rank metric coding theory. So in our work, we also define a new problem. We call it rank support basis decomposition problem. So the idea of this problem is now we are given a vector space X. So this vector space, in fact, is a product space of A and B. So the question is, can we find A and B such that the dimension will be satisfied and also A dot B will be equals to X. So that's the problem for the rank support basis decomposition problem. And we also define this advanced rank support basis decomposition problem. So similarly, we are given this W, a vector space of this form. Are we able to decompose it into U plus AB that fulfills all the conditions over here? So that's one of the problems that we define in this paper. And in fact, from this, we can easily see that, in fact, all instances in RSBD are instances in RSBD plus, because you can just take U as equals to 0 space, then it is equals to, the RSBD is equals to RSBD plus problem. So in fact, we have solving an RSBD plus problem is as hard as solving an RSBD problem. And in this paper, we also talk about some strategy to solve this RSBD problem. So we have a combinatorial attack, and our best solving complexity is of this exponential form. While we also consider an algebraic attack on this problem, so we propose a modeling into a multivariate quadratic system, and its solving complexity is exponentially high. So the details will be covered in the paper. And under all this assumption, we have actually showed that our MURAVE has achieved EUF-CMA security in the random oracle model. So finally, I'm just going to highlight the our parameters performance. So if you just look at this blue table, we have our public key size is about 5.33 KB and 1.24 KB for our secret key size and 9.69 KB for our signature size. And this is a table that compare our performance with some other signatures in RAM metric. So for the first one is our proposal, and the second one is Durandal. Durandal is proposed in the Eurocrypt last year, and it is a Schnorr type signature scheme with Fiat-Charmé aborts. And the public key size is about 15 KB, and which is larger than our proposal, but their signature size is better than our proposal. And also for some comparison, we can see that for these two type of signatures, their signature size are generally bigger than other type of signatures. And also we also modified the implementation codes for Durandal, which were implemented in C++ and based on NTL and GMP. So we have actually tried to compare our performance with Durandal. So we actually see that as you can see from this table, our signature generation time is much faster than Durandal. So the reason of this because in Durandal it involves solving linear system at this offline stage, and also it requires Fiat-Charmé with aborts, because at each signature generation there's a success probability of about 0.135. Therefore, they need to repeat a number of times at each of the algorithms. So whereas for our signature scheme, basically we just involve polynomial additions and multiplications and inversion only. So that's why that explains why our signatures is much faster. So I'm going to conclude the presentation. So I've basically talked about some adaptations and challenges in Schnorr signatures in RAM metric, and also I've described the MURAVE signature scheme, and also talk about its security by defining some new problems, and under this assumption we have achieved EUF-CMA security. And finally, we have compared the parameters and implementations with other signature scheme. And so actually we just to highlight that we purposely made our parameters aggressive, because we want to attract attention for the community to study about the hardness of RSVD and RSVD plus problem. So whether are there any other attacks on this problem, so that we need to look at the security as well. And also another interesting thing that we can look at is the application of this RSVD problem in code-based cryptography. So basically that's my presentation today. So is there any questions?
Yes, thank you.